comes to an end is, interestingly, because there is no growth. No growth is no longer possible with a capitalist system. Because the rate of return, the private rate of return on investing, on taking entrepreneurial risk has become too small. Right? There's no profits. The system is collapsed. You have to reproduce the means of production. That's very costly. The margin you get out of it, because of decreasing return, because is small. And so you have to socialize everything. It's unclear, you know, if you read, it's worth reading. There's a lot of fumbling there. Fumbling and he's trying to, in fact, the math doesn't work. The math is useful. The algebra doesn't work. Okay? The math doesn't work because it's unclear why, if that's a technological fact, how the hell do I get to remove the technological fact by changing the system of property rights? Right? If I get to the point in which I invest 100 and I get no return, basically, I get zero profit because 100 produces 1,000, but the 1,000 is all consumed either by intermediate product or by wages of labor, right? What's the point of investing? And why should the workers at that point, even if they own the means of production, to keep investing and saving, given that they have no return? Why shouldn't they just increase consumption and invest less? Right? What's the point of investing if there's no reward from investing? This doesn't depend who owns what. Even the central planner would not invest if there's no return from investing. Right? But anyhow, I don't want to go there, but it's worth thinking. The point is that these guys have their neoclassical production function in mind. Right? They have their neoclassical production function in mind. Right? Do you see what I mean? They really have it. And the world they're thinking on is therefore a world of steady state. Eventually you accumulate capital over time, labor may grow, exogenously or endogenously, and land, there is a given amount, but you put the land progressively into usage, a la Ricardo. If this is not obvious, well, I'll be happy to write the formulas. If it is obvious, we go on and write formulas in a moment. Okay? Eventually you get to a state in which all the usable land has been used, right? Labor may be growing. Let's write a dynamic version of this, right? Right? And this may be growing, but it's growing somewhat exogenously. The labor force. Right? Other, we'll see in a moment, I've been thinking of how to endogenize N, right? How N depends on this and that and consumption and so on. But at the level of, say, Marx or Ricardo, you know, Marcus is the only one that kind of focuses on that, right? This just grows. And since then, right or wrong, most growth theorists have taken that as given, which has been funny for a while. I think we've now been living for a few decades in a world in which it's worth asking about that, and how endogenous it is. So this grows at that rate, and as long as K also grows at the same rate, so that KT, LT is a long-run constant, right, because they grow at the same rate, then the system goes at the steady state. Okay? In fact, the way we rationalize it is to say, look, there are constant returns to scale. Right? And if there are constant returns to scale, we can try to express everything in per capita unit by dividing through by labor. Okay? Malthus' version is what? Malthus is, well, N is really not constant. So when there is little L, given K, and given land, L is scarce, gets a bigger wage. When people get a wage above a certain threshold, they have a lot of sex, they make a lot of children, they don't kill them, they feed them, so population growth, but that means a generation or two later, we got a lot of people working. Or maybe actually people migrating to that area where the wages are high, trying to, because they hear, oh, in Lancashire, wages are high, in the province of Siena, wages are high, let's go work there, right? And then wages go down, and the thing goes back to the states. That's the view, okay? And that's the view all along. That's the view also in the second half of the 19th century. So the so-called neoclassical, Marshall, Gibbons, Edgeworth, whatever, don't really they contribute a lot, they focus on a lot of analytical tools that we eventually use. Marshall gives us a beautiful way of thinking at competitive equilibrium and various forms of market equilibrium in a given industry, monopolistic, blah, blah, blah. The view, the overall view of the growth process doesn't really change. We'll talk Thursday where it changed. It changed with Schumpeter. There's no doubt that Schumpeter, from that point of view, is the first of the old economists that before everybody else sees the limit of this as an empirical tool. I mean, his is an empirical observation, and it's not by chance that it's somebody that has gone through and has experienced already the end, if you want, of the first industrial revolution, that is seeing the second, with the development of the chemical industry, the electric engine starting to take all, the diesel cars that are starting to be around, and sees, wait a second, this stuff, it's not going to end that quickly. It's been going on for 2 centuries now, and it keeps going, and the kind of stuff I'm seeing at the turn between the 19th and the 20th century is really heavy duty respect to the past. Maybe there is something going on here, let's try to think about it. So we'll talk about Schumpeter maybe at the end today or Thursday. So let's try to get some analytical tools out of their way of thinking. So the first thing that we want to think about that they use and understand what it means is the idea of constant return to scale. Okay? So let me try here to give you something that the profession has lost, but it's very clear in all the classical theorists of the 20th century. It's extremely clear in the people doing general equilibrium theory. It's extremely clear, particularly for Neumann, in Mackenzie, in all people looking at production theory between the two wars, then at the Coles Commission, and then in the 50s and 60s. There is the constant return to scale in the theory, at least in the abstract theory of competitive equilibrium. It's not really a strong assumption. It's a kind of trivial consequence of the assumption that the engineer has listed all inputs and all outputs in the production process. And here you want to make a note and think about this. In the theory of competitive equilibrium, and in general, in the classical theory of growth, there is one object that is dramatically absent and about which we don't theorize much, and that's the firm. There are no firms in competitive equilibrium. Okay? The entity called firms, with an entrepreneur, there is a residual claimant, there is a specific individual, a specific characteristic that has access to a knowledge of specific technology but that's not there. Classical competitive equilibrium theory is built around if you want, a more primitive notion or a more abstract notion, but is independent or abstract from the existence of firms. So let's try to get this piece of theory clear in mind, because it's useful sometimes to go that way and it's risky some other time. But we better don't get confused. This is clearly John Hicks, which kind of pointed out the guy that gets it very clear in competitive equilibrium is actually Lionel Mackenzie, that not by chance in all his existence proof always refuse to assume that there exist firms, saying, well, firms are an endogenous phenomenon. Firms are an economic phenomenon. They're not given by nature. Individual preferences are given by nature, from the economist's point of view. Where nature here includes culture, includes your tradition, but the technology is in some sense given by nature, if I take it as given, if I'm not studying technological change. But firms, no. Firms are the most, are an economic phenomenon. Firms are created and dissolved. Firms are the outcome of an equilibrium phenomenon that responds to economic incentive. We need to have a theory of the firm. We can't assume firms. Which is why, if you look at the early existence proofs, that's why Lionel proof of 1954 is already superior to the Arrow-Debreu proof, which is in fact a sloppy proof, because look at it. Or even read theory of value. You should read theory of value to see the mistakes and the limits. They assume there are firms. It's even worse. They are forced to assume that the end consumers, see, I'm giving basic general premium here as understood. So if it is not, you better raise your hand and say it. In the Arrow-Debreu approach, it's very misleading. It should be, we should stop teaching that. It's not the right way of teaching. Yeah, think of the way it is. There are end consumers. Each consumer has a set of preference order, right, over the commodity space. But each consumer has an endowment of goods, right, and shares of the firms. That's totally insane, right? Maybe bored with my labor time. I may pretend that I'm bored with 2 kilos of sugar and a house and 3 cows and 1 chicken, right? But that's even a stretch. But to assume that there are firms and we're shareholders, we're buying and selling shares is what financial economics, which is a part of Jack Rillo theory, is all about. It's a bit preposterous. And assuming that firms are there with their decreasing return already in place, it's really throwing away a problem by making a super strong, incredible assumption. As a starting point, fine, but we better understand that that's a super strong assumption. So the way classical theories think about is, and if you have time to go study those years, it's very interesting, is in terms of activity analysis, which is something that is brought into economics in a visible way by Jalin Koopmans and the Coles Commission, that before it's used by John von Neumann and the Austrian group, Wald and so on, in their 30s articles. And before that, it's in some form in Varra. If you read Varra element, you will see, the guy is an engineer, and the way he describes, he talks about firms, but his firms are production processes, and he has these linear things, and this is, well, here, production process is a whole list of things we put in, and a whole list of things that we come up. That's essentially a very reasonable way, I believe, of starting to think about production, right? When I think about production, what's given to me at any point in time is a collection of possible production processes. And an incomplete, but I think useful way of starting to represent a production process is by saying a production process is an activity, A, and an activity is a list of input and a list of output. So an activity is a list of input xt in some n-dimensional space, right? And this, sorry, a period later, and we'll have a talk in a moment about period, produces a list of output. Let's put it also in the same space. It's just big n, large enough, so everything is in there. Each one of these vectors will contain a lot of zeros, but who cares? Okay. Now, how much real time, clock time, watch time goes between t and t plus 1 depends on how much we are breaking down processes. This is a classical problem in equilibrium theory. People have worked for years about that. There's a whole theory of capital related to time and the length of processes developed by Bombaverk and other German-Austrian group. May or may not have relevance. I never quite understood if that insight is relevant or not. There is an extent to which it's relevant in the sense that obviously if we look at production processes, even from the point of view of final utilization, right, say consumption, it's clear that some production processes that get us a final consumption good are very short, others are very long. Okay? It's also true that I can take the shortest of them all that I can describe and break every one of the other into intermediate steps so that all processes the same length. Right? All I have to do is to reclassify intermediate goods and make them as final goods. You know, so I have to build, if I have to build a car, it takes a day. I can break it down to 24 processes, each one lasts an hour, which is how long it takes to make a pizza. No, it takes even less. Well, if you put the dough, maybe it takes a few more hours than an hour. Anyhow, whatever. Say the minimum process is an hour, and for about the example appropriately. You know, I can break down the build of a car into, you know, 24 things, 23 of them as on intermediate product, no final consumption good, the 24th as the final consumption good that you can take away. Right? So, I don't know, anyhow, if you're curious and you go look at Bambaberg and all that, you will find a gigantic discussion about this. And it's a discussion also Schumpeter somewhat undertakes because it belongs to the same cultural group. I don't think it's produced much. Hayek has it, many of them have this discussion about the role of time, which they connect to the rate of interest, to the discounting, to the rate of return on capital, capital is time. In the abstract, it's all true. Analytically, I haven't learned much. I'm always happy to be told that there is some insight I can get from treating capital as time and time as capital that I do not get from the standard model, but I haven't, okay? So let's just assume that we have normalized here. So in activities like that, and the observation is that an activity is essentially attached to a technology and to specific capital goods, right? So I can think of the activity that takes a pot, a liter of water or less, half a liter, one egg, okay? 12 minutes of my time and a certain amount of gas, okay, to cook a boiled egg. That's an activity. It's got inputs, it's got outputs. Among the output there is the boiled egg, but there is also a bowl drink that has wasted 15 minutes, and there's also some hot water. So the list of output is not always a scalar, it's most often a vector. And actually there's also the dirty pot, okay? Okay? That's an activity. And the point here that you want to observe is that there is also, given that I want to boil an egg, there is an appropriate, efficient scale at which to do it. There is an appropriate pot. You don't take a gigantic pot to just boil an egg, you get the smallest pot you have at home. And you don't take a big fire, take a small fire, right? And you do that because doing otherwise would be wasteful. Notice that in observing this, you're already observing an economic assumption. You're observing that there is free disposal. Right? What does free disposal mean? Free disposal says that given a certain level of input, I can produce a certain level of output, and every other output below that, because I can dispose of. So I can waste water and eggs, throw away everything and keep just one. Okay? But to the extent that the resources I use and the output I produce a positive value, I'll try to use the efficient. So the little pot is the appropriate one. Now what if I want to produce 2 eggs? The observation here is that there is at least one simple way of producing 2 eggs, is to replicate, to do twice what you do to produce 1 egg. That is, you take 2 people, 2 15 minutes each, 1 15 minutes each, so 2 15 minutes, 2 eggs, 2 pots, 2 half liters of water, 2 fireplaces, and you boil 2 eggs. It's called replication. And you get exactly twice the output from twice the input. You can do it 3 times, 4 times, okay? What's the assumption here? The assumption that I'm using is each factor of production can be replicated. No one among the factor of production is bounded by nature. But as long as I can keep replicating, there is constant return by definition. So the point is to observe that per se, if I take the notions of activity analysis seriously, constant return to scale for a given activity is a triviality. It's not a strong assumption. At least in principle. Notice that the only thing that can stop this is that at a certain point I run out of X, or I run out of fire spot, or I run out of water, okay? But per se, the mathematical description is just what? It is what we call, let's use your imagination. Here is Rn, we put X here. Here is Rn, imagine any dimension. And given that vector, I get 1n, right? That's my initial activity. It's represented as a point, right? Let's call it x at level 1 and y at level 1. That's the unit level